In 1923, Hermann Oberth, a German scientist, in a book entitled The Rocket into Interplanetary Space, put forward a dream. If we could look at the heavens with an astronomical telescope in orbit, unhindered by the shielding sea of atmosphere that blankets the Earth, think of the discoveries we would make, the clear vision of the universe we would have in quiet space. The telescope, an instrument for collecting more light than would normally enter the human eye. For over 300 years, light, optics, and the human imagination have sculptured our perception of the universe. Today, large telescopes, such as those at Palomar Mountain and Kitt Peak, carry out detailed investigations of very faint objects at the limits of perception. The naked eye has been replaced by spectroscopes, photographic plates, computers. Yet a fundamental challenge, a link between past and present, remains ever constant. The quest for more light, to see fainter and more distant objects, to construct better light collectors.
This is a photograph of the galaxy Messier 33, a nearby galaxy, a rather common type, and quite illustrative of the type of image that we obtain with telescopes that are based on the surface of the Earth. This type of information, together with spectra, like the plate that I'm holding here, form the largest part of the information obtained and used by ground-based astronomers. It's quite good, but nowhere as good as it might be. Astronomers themselves, and many in the lay public, don't appreciate at times the enormous distances that they're dealing with. When we look at the photograph of a cluster of galaxies like this, it's hard to appreciate that these images that we obtain now are from galaxies that are probably 1 billion light years away. With the Space Telescope, we'll be able to look to much greater distances and therefore much further back into time. In fact, much closer to the creation of the universe itself. In order to understand how the Space Telescope works, we really need to understand how the astronomer and the astrophysicist work with light.
Almost all the information we have about the universe reaches us in the form of electromagnetic radiation, which objects either radiate, absorb, or reflect. The spectrum disperses this radiation into its separate colors: visible light, infrared radiation, radio waves at one end, to X-rays and gamma rays at the other. Now, each element in nature has a characteristic spectral signature, a fingerprint of light, if you will. Because common earthly elements have been found in the sun and stars, we can determine through a star's own unique stellar spectrum the speed of an object, its temperature, density, chemical composition. Each band of light becomes a window onto the universe with a unique view. But many wavelengths are permanently inaccessible to astronomers using earthbound telescopes due to the Earth's atmosphere, which, in shielding us from most of the biologically harmful radiations, allows only visible light and varying amounts of ultraviolet, infrared, and radio to reach the ground. we are given a very incomplete picture of the universe in these wavelengths. Our stellar fingerprint is difficult to analyze. The atmosphere also frustrates ground-based optical observations. 100 miles deep, it is filled with dust particles, water vapor, and other obscuring materials. Constantly shifting layers of air of different densities bend light back and forth. Atmospheric turbulence imposes a fundamental limitation on a telescope's ability to see clearly two objects close together in the sky. At times of bad seeing, stellar images waver like candle flames in a gentle breeze. The Space Telescope will be out where the images are completely quiet, where the full spatial and wavelength resolution powers of the telescope can be used. It will peer far into the ultraviolet and infrared regions of the spectrum. A galaxy seen through the Earth's atmosphere as a big, shimmering fuzzball in space will be brought into sharp, clear, and steady view for study and analysis. We will see it 10 times clearer than we see it now. We will see 50 times further into the universe than the best ground-based telescopes can see. All this from a telescope no different in principle than the reflecting telescope of Newton and his descendants.
Every optical telescope operates in essentially the same manner. It gathers a part of the light produced by or reflected from an object, concentrates this light in a single area, the focal plane, and then magnifies the image formed there.
So in space, as on Earth, we must begin with a mirror. In this case, polished to within 1/2 a millionth of an inch in accuracy. As light enters from space, something must catch the reflection of our primary mirror. A secondary mirror is set into place. An image must now be fed into a variety of auxiliary instruments. So we provide a package of 5 major scientific instruments which will convert telescope images into useful data. The scientific instruments and optical assembly must then be encased in a shell which protects them from dangers in the space environment, such as stray light or micrometeoroids. To power our telescope, we turn to the sun for energy and attach solar array panels. In the Earth's shadow, we will power our telescope by batteries. Finally, we must have a means of communicating with our telescope, so we obtain 2 high-gain antennas. Data which these antennas beam back to Earth will be converted to pictures.
The 200-inch telescope here at Mount Palomar in California is only about twice as big as the Space Telescope will be, yet it's very much more massive because, of course, it has to work in the Earth's gravity. However, all telescopes, including this one and Space Telescope, are essentially the same. They gather light so that we can analyze it with various instruments. The Space Telescope will have 5 such instruments. There will be 2 wide-field cameras which take pictures of the sky, one over a wide region and another over a smaller region. The smaller region camera will have much higher resolution than the other. There will also be 2 spectrographs aboard Space Telescope. One will be used on fairly bright objects and take the highest resolution spectra. The other will be used for quite faint objects, such as galaxies and faraway quasi-stellar sources. There will also be on Space Telescope an instrument that utilizes the fine guidance system of the telescope. This is the system that keeps the telescope pointed quite accurately at the stars during an exposure. This instrument will allow us to measure the distance between stars quite accurately on the sky, and also their motions over a short period of time.
The Space Telescope, due to be launched in the 1980s, will be hoisted into orbit some 500 miles above the Earth by the Space Shuttle. Fitting into the shuttle's cargo bay, the telescope will be latched to a tilting mechanism and rotated into a 90-degree position for checkout. It will then be placed in a vertical angle, released, and its power and communication systems deployed. The periodic revisit of the shuttle will allow for the replacement of components and routine maintenance. Every 5 years, the telescope will be returned to Earth for major ground refurbishment. This ability to service the telescope through human care will extend its lifespan up to 20 years.
It will orbit above our murky atmosphere and obtain images of objects that are incredible distances away, perhaps of galaxies 14 billion light years distant, so far away that when the light first set out towards us, there was no Earth, no Sun, no Milky Way galaxy. We will be probing the time of the earliest history of the universe. Space Telescope is, in a way, a little like Galileo's first telescope. Wherever Galileo pointed his telescope, he made major new discoveries. Look at the moon, you find mountains and craters. Look at Saturn, you find rings. Look at the Milky Way, and you find it is littered and composed of stars. Every one of these discoveries, things that people had not known before. I think it's going to be very similar with the Space Telescope. It will illuminate celestial objects that we know about. It will discover celestial objects never before guessed. It will provide insights into the most important questions, such as stellar evolution, such as the search for planets going around other stars, and the grandest cosmological questions of the origin, nature, and fate of the universe. Space Telescope is a kind of grand intellectual adventure for all of us, which will cast light not just on the cosmos, but also on ourselves.
It's impossible to predict what the Space Telescope will bring in terms of its results, but we do know the results will be exciting. When the first radio telescopes were built, we did not know that we would find quasars and pulsars. Or when the first X-ray telescopes were built, we did not know that we would discover X-ray stars. With Space Telescope, we will find many new things. We'll find exciting things.
Stretching the mind of humankind to the very beginning and end of space and time, the Space Telescope may tell us at last whether the universe will expand forever or whether that expansion is slowing. It may help us learn more about the violent events of the universe. Pulsars, quasars, the gravitational implosions that produce black holes. It may also tell us how the universe began and how it will end. But ultimately, as is the case with all voyages of discovery, its greatest contribution will be the unexpected breakthrough that brings completely new knowledge. For with the Space Telescope, we will shake loose of the Earth, of its murky and oblique atmosphere, and in the never-ending quest for light, we will soar